go from there.
Okay, this one says, show the conjecture is false by finding a counterexample.
Okay.
And it says, the average of any two consecutive even numbers is an even number.
Okay, you can show that's false if you can find even one case that's not true. In other words, when they make this conjecture, they're saying it's always true, the average of any two consecutive even numbers. Well, can you find two consecutive even numbers whose average is not even?
Can you tell me what consecutive is?
Next to each other, in other words, consecutive numbers would be 1, 2, 3, 4, 5, 6, 7, 8. Consecutive even numbers would be 2, 4, 6, 8, 10. Consecutive odd numbers would be 1, 3, 5, 7, 9, so forth and so on. And this is a fairly common term, consecutive for numbers. In number theory, it's very common.
Okay.
So the best way to do this is just to take two consecutive even numbers, find their average, and see what it is.
Okay. So like 1 and 2?
Those are not consecutive even numbers.
Okay.
In other words, both of them have to be even. Both of them have to be evenly divisible by 2.
Okay, so like 4 and 6.
There you go. What's the average of 4 and 6?
5.
There's the one case you just came up with that disproves this conjecture.
Gotcha.
Turns out that any two consecutive even numbers, even if I took 2 and 4, that's going to average 3. If I took 6 and 8, it's going to average 7. In fact, the average of two consecutive even numbers is always odd.
Okay.
In other words, if I were to change that to odd, you wouldn't be able to disprove it by finding, it's much harder to prove something in math than it is to disprove it.
Gotcha.
If I wanted to prove that conjecture, it would be hard to do. Because no matter how many cases I can come up with, and all of them are odd, it doesn't prove that they're all going to be odd. You can't. Whereas the other case where I said that it was even, the only thing I have to do to disprove that is to come up with one case. And that's the beauty. It's much easier to disprove something than it is to prove something.
Gotcha.
This is true, but I would hate to have to prove it. You have to use mathematical induction to prove it. And that's really difficult conceptually. So let's not go there. But what do you got next?
Okay, the next is different. It says, complete the following proof by completing the matching in the reason section.
Okay, can you have you taken pictures and sent them to me before?
No.
Let's do it.
Okay.
Because after you do it the first time, the second time is so much easier. Take a picture of that because it's going to be too much to verbalize. A typical proof would be...
Can I do this with my phone?
Take it with your phone and send it to my email address, which I'm writing on my screen right now. And then I'll be able to bring the picture up on my desktop and we can both go through the proof.
Gotcha.
Unless it's out of the book, and then you can just name a page and I can probably find it. But I'd like to go through the process of having you send me a picture anyway, just to get it completed, and then it'll be easier to do if we have to do it again. And at some point, you're going to need to do it. That's just the nature of geometry. There's too many questions where they give you a graph or a figure and they ask you questions about it. Well, do you have an iPhone or an Android phone?
Android.
One of the few. So, do you know how to take a picture and send it to an email address?
Yeah.
Okay, I figured you probably did. I think it's a little easier with Android. With an iPhone, you have to make sure you specify that use the large image size when you attach it. Otherwise,
Oh, really?
yeah, otherwise it sends it and I'm unable to read it. So, let's see. Even as, the iPhone's camera is terrific, but it does force you to do that one option.
Right.
And now, the next time you need to send me something, you can just type DA and it'll bring up my email for you.
Okay.
Okay,
Awesome.
so you won't have to type in the email each time. You just need a couple of letters. Let's see, which one are we doing here?
Number 29.
Okay. So it's giving you all of the statements and it wants you to put the order of the reasons in proper order.
Yep.
Well, this is a little different. Proofs are tough, really tough.
Okay.
But they're not so tough to learn if they give you at least one, either the statement or the reason. In other words, we're going to get one. Number 30, they don't give us anything in order, so we'll have to come up with all of those.
Okay.
And there's a few in your book where they'll give you the statement. In other words, they'll give you one statement or reason for each row. And then you have to come up with the other. And that's a nice way to learn how to do proofs. A bad way is when they give you nothing. In other words, if you had to prove this thing from scratch, it would be really, really tough. And it would be like trying to teach how to ski by dropping you on the expert slope. Okay? Just not the way to do it. This is not a bad way here. I kind of like this because they give you multiple choice. So it's pretty easy to figure out this one. 30 is going to be harder, but not that hard. So let's take the first statement. Angle S is a right angle. That angle is 40, and the other angle is 50. What can I say for a reason for that? Those three things.
Sure.
Which of those answers fits?
Give me 1 second, sorry.
It's all
right. I guess you could say given.
Yeah. In other words, everything that's made in statement 1 is under the given, right there.
Gotcha.
So that's that one. Now, angle, the measurement of STU is equal to the measurement of RTS plus the measurement of RTU. Which one would you think would be the right reason for that?
Would it be the angle addition postulate?
Yeah. Let's see. Have you seen this page?
Yeah.
Well, they kind of repeat this page throughout the geometry book. It applies to real numbers. It kind of applies to angles. It applies to line segments. The first 4 of these things are obvious, kind of. In other words, if A equals B, then you can add anything to both sides of that equation. Therefore, A plus C equals B plus C. That's the addition property. Straightforward, same with the subtraction, same with the multiplication, same with the division. Those four properties basically tell you that you can do whatever you want to one side of an equation as long as you do it to the other.
Okay.
Okay? The ones that are hard to remember are these four.
Okay.
The reason they're hard to remember is because they don't really make much sense. I mean, this first one, the reflexive property, merely means that A is equal to A. And that's what I mean, that they don't make much sense. And you wouldn't think you would need to prove that A was equal to A as a statement and then say it's because of the reflexive property. But sometimes you do. Okay? Mm-hmm. And the symmetric merely means that if A equals B, B equals A. The transitive, if A equals B and B equals C, then A equals C. And the substitution, if A equals B, then A can be substituted for B in any equation or expression. So I would say try to memorize those four right there.
Okay.
Because those are liable to come up.
What page are you looking at right now? That.
Yeah. What page is that? I have the same book you have, but I'm not sure I have the same edition. So it could be a different page. But hold on. I'm looking for it. I took a picture of it. It's page, in my book, page 96. Chapter 2.4.
Okay, thank you.
I don't know if that's in your book or not, but and you'll find it eventually. In other words, your geometry book is full of these rectangles that have this green heading. That's for theorems, postulates, anything that is stated to be true. Somebody has proved it, but you're expected to just be able to recognize those theorems when you need to. Now, let's go back to this. So that was the angle addition postulate. Notice that that's kind of similar to the addition property for real numbers.
Gotcha.
Number 3, the measurement of angle STU is equal to 40 plus 50.
Would it be substitution property?
Correct. Number 4, the measurement is equal to 90.
Definition of right angle? Is that right or no?
I don't know. I'm sitting here thinking, I don't think so. I think that is the simplify?
Simplify. Oh, okay.
I mean, it's not substitute. It's not the right angle congruence. I can't say that that's a right angle yet. All I'm saying is that it's 90 degrees.
Yeah, and that has to be number 5.
Right. And the next one says that, therefore, angle STU is a right angle. That's the right angle definition of a right angle. The definition of a right angle is if it's 90 degrees, it's a right angle. Okay, so for 5, it's C. And finally, for 6, angle S is congruent with angle STU.
Has to be the right angle's congruence theorem?
Right. In other words, the right angle's congruence theorem says that all right angles are congruent. Okay? I mean, it seems rather silly that there's a theorem that says that. It's like saying all angles that are 47 degrees are 47-degree angles. But nonetheless, that's the reason proofs are so tough, is because some of these just don't seem necessary.
Gotcha.
We did the simplify, didn't we? I think
Yeah, that was
we assumed
4.
that 3 was simplified. Or 4,
4
rather.
simplified.
4, right. In other words, is all we did was we simplified this. Instead of 40 plus 50, it's 90.
Gotcha.
All right. All right, so now we go to a little harder ones. Let me say this, since you've missed quite a bit of school, the toughest part of geometry is the proofs, without a doubt. Of the whole semester, or the whole year, the toughest part you're going to get is the proofs. Okay? And you're going to be done with them very quickly.
Okay.
And you will never have to know them again. In other words, when you take your ACT test or your SAT test or whatever test to try to get into college or anything else, they do not test you on proofs. So you get them in the first 2 or 3 months of geometry, and then that's it. So if you can get through them, you will be done with them.
Gotcha.
Okay. So let's see if we can do this. What's the reason for number 1?
Given.
How about number 2?
I don't know.
Definition of complementary. In other words, if angles 3 and angle 2 are complementary, by definition that means they add to 90 degrees. Number 2 says they add to 90 degrees because we were told that they are complementary. So this reason is definition of complementary. Number 3, angle 1 plus angle 2 equals angle 3 plus angle 2.
Would it be the reflexive something? I forget.
Yeah, you're not that far off. Hold on, let me look at it for a moment here. Let's see. Angle 1 plus angle 2 equals angle 3 plus angle 2. How? In other words, in this picture, 1 plus 2 does not appear to equal 3 plus 2, but let's see if we can figure out why that's true. Oh no, we're trying to prove this. 1 plus 2 equals 3 plus 2. Okay. 1 plus 2 equals 90 degrees. 3 plus 2 equals 90 degrees.
If they were to equal 90 degrees, wouldn't that make 2 and 1? When they put a right angle symbol there?
Well, yes, although that's, in this particular case, that's not particularly necessary. You would think they would have, but they've told you that 1 and 2 add to 90 degrees here. But they've also told us that, hold on a minute. I had my train of thought there for a second. Wow. Hold on. Oh, I know what it was. Yeah. In other words, if 1 plus 2 equals 90 and 3 plus 2 equals 90, then 1 plus 2 must equal 3 plus 2. Let's see if we can figure out the property. Wonder if that property is... See, that's the thing is that even I don't memorize these properties. let's see. They're both equal to 90 degrees, therefore they're equal to each other. That is the transitive property. Notice what the transitive property says. It says that if A equals B and B equals C, then A equals C. Well, in our case, we have if angle 1 plus angle 2 equals 90, which it does, and angle 2 plus angle 3, which is the C part, equals 90, the B part. In other words, 1 plus 2 equals 90, and 90 equals 2 plus 3. Therefore, 1 plus 2 equals 2 plus 3 by the transitive property. So the reason in number 3 is the transitive property. Probably the transitive property for angles, because this thing I showed you was the properties for real numbers. And angles have these same properties, line segments have them, and right now we're dealing with angles, so it would be the transitive property of angles.
Gotcha.
And for number 4, how do I get angle 1 equals angle 3? Or the measurement of angle 1 equals the measurement of angle 3?
Would that just be simplified?
Not quite. We would need the subtraction property. In other words, notice how we get that. We get it by subtracting angle 2 from both sides of that equation. Once you subtract the measurement of angle 2 from both sides, you're left with measurement of 1 equals measurement of 3. So that would be the subtraction property for angles. And finally, to say that angle 1 is congruent to angle 3, definition of congruency. And that's all you need to say. Let's talk for a second about why they use different words to mean the same thing. In other words, what's the difference between congruent and equal? Because you have a lot of theorems that say that if two angles are congruent, then the measurements are equal. Okay, well, what if I have an angle like that, and over here I have an angle like that? It's hard to say that those two are equal. In space, they don't look equal. One is rotated relative to the other. Okay? So I would say that that is congruent to that. And what that means is that the measurement of that is equal to the measurement of that.
Okay.
Okay? And that's really the difference between congruent and equal. In other words, if I say this triangle is equal to this triangle, then I would expect it to look exactly the same. The right angles in the same position. These would be equal. But if I draw this triangle, same triangle, but I rotate it slightly,
it would be congruent.
Then they're congruent. And congruent for triangles means same measurement on the three sides, and all three angles are equal. You haven't got to congruent yet, but here's what they use. Are you familiar with these tick marks and angle things like this?
Kind of.
Well, what this means is that angle is equal to that angle.
Okay.
If I want to say this angle here, I got to use two hash marks. That's equal to that angle. And then this one down here is a third angle that's different than the other two. So I would use 3 marks, and that's equal to that. So if these two things are congruent, then the measurement of their angles are the same, And furthermore, the measurements of their sides are the same. A single tick mark through the side means the measurement of that side is the same as that one. That's a different side, different measurement, but it's the same as that one over there. And finally, we have a third side here, different measurement, but the same as that side there.
Gotcha.
Right? So when you do get to the chapter on congruency, which is chapter 4, after proof or perpendicular and parallel lines, this is what it's going to be about, is that. Because you can have congruent triangles and you can have similar triangles. A similar triangle would have the same 3 angles, but not the same 3 sides. So that's the difference between congruent triangles and similar triangles. Okay? Similar, same shape, different size. Congruent, exactly the same shape, exactly the same size.
Could you help me understand like angle types, like corresponding, alternate interior,
Yes.
consecutive interior?
First of all, let's talk about the really important stuff about parallel lines and a transversal.
Mm-hmm.
You create 8 angles. When I draw that transversal through those 2 parallel lines, I create these 8 angles.
Mm-hmm.
But there's only 2 unique angles, 1 and 2. Every other angle there is either 1 or 2.
Okay.
And the way you can kind of tell is notice that 1 is obtuse, 2 is acute.
3 is acute and 4 is obtuse.
3 is the same as 2 because it's acute. 4 is the same as 1. It's obtuse. What's 8 the same as?
4 and 1.
Make it the same as either 1 or 2. Yeah. So it's the same as 1, right?
Okay, yeah.
About 7.
2.
About 6.
2.
Okay, good. In other words, all you have to do is figure out which is the acute one, which is the obtuse one, and you're done.
Gotcha.
And the only other thing you really need to know here is that 1 and 2 are supplementary. They're always going to add to 180. Why? Because they're a linear pair. In other words, whenever you have a line and an angle, these 2 angles, A and B, are always supplementary.
Gotcha.
Okay. Now, in geometry, they insist upon talking about alternate interior, alternate exterior, consecutive, and corresponding. So let's go through that. The easiest one is alternate interior. Interior means between the parallel lines. Alternate means they're on opposite sides of the transversal. So that one and that one are alternate interior. And the theorem says they're equal. Well, we can look at it and see that that's true. In other words, based on what I told you, here's the problem. If I gave you a problem like this and drew a line like that, now it's not so easy to tell the obtuse or the acute angles. So now I would need to know that A is equal to B because they are alternate interior angles.
Okay.
Okay. 4 and 5 are also alternate interior angles. You see why?
Yes, because they kind of alternate.
Yeah, they're on the opposite sides of the transversal, and they're both inside the 2 parallel lines. So 3 and 6 are alternate interior, 4 and 5 are alternate interior. What would 1 and 8 be?
Would that be alternate exterior?
Yes. Exterior means they are both outside of the 2 parallel lines. They're alternate because they're on opposite sides of the transversal.
Okay.
Okay. corresponding. 6 and 2 are corresponding and equal.
Yeah.
1 and 5 are corresponding. What's corresponding with 3?
7.
Correct. In other words, the theorem says is that the corresponding angles are equal. And we can see that 7 is corresponding with 3, and therefore it's equal. But up here in this picture, and I'm drawing that not knowing whether that's a right angle or not, but corresponding would be A and B, and those are the two that are equal.
Okay.
Not A and C. A and C are not corresponding. Okay? And the last thing is consecutive. Well, that's pretty easy. In fact, the theorem probably says consecutive interior.
Yep.
Well, it says consecutive interior angles are supplementary. Well, that would be 3 and 5. They're consecutive, right? You can see why they're consecutive.
Yes.
Okay, and they're interior because they're in between the two parallel lines. You could say that 1 and 3 are consecutive. They're certainly next to one another, and they are supplementary. So I don't know if that they're not consecutive interior angles, but they're consecutive angles.
Okay.
So you might say that all consecutive angles are supplementary in this picture here. Not as a matter of course, but in this picture. Now, for years, I've taught geometry, and the only thing I've taught people is find the acute, find the obtuse. All acute angles are equal to one another. All obtuse angles are equal to one another. And I felt like it wasn't really necessary to memorize all those 4 theorems. But in this picture over here, it kind of is, because you can't really tell which is the acute and which is the obtuse. So you kind of have to know that alternate interior angles are equal, therefore A and B are equal. Consecutive angles are supplementary, therefore A and B are supplementary, and so forth and so on. In other words, you can't, even though 95% of the time when you run into a problem that's parallel lines and a transversal, it's going to be in an angle. And so you're always going to be able to figure it out without knowing any of those 4 theorems.
Okay.
When you take your ACT test, there are at least 6 problems that have parallel lines and a transversal. And you don't need to know anything about alternate interior or alternate exterior, because they always draw it at an angle such that you can immediately figure out the acute and the obtuse, and then the problem's easy. You don't need to resort to those 4 rules.
Gotcha.
But if perchance you should find yourself looking at a problem like this, and all the angles are labeled A, B, C, D, E, F, G, H. Tell me which angles are equal to A.
E.
Good.
These
E because they're corresponding.
Everything is corresponding?
No. A and E are in the same position relative to that transversal.
Gotcha.
Okay? So that makes them corresponding. And then the theorem says that corresponding angles are equal. What else is equal to A? There's 2 other angles that are equal to A there.
D and H?
D, because those are vertical. In other words, whenever you have 2 lines that are like that, then that's 1 and that's equal to 1 and that's 2 and that's 2. Okay, so vertical angles are always equal. So you don't need any of the geometry theorems to show that A is equal to D. And
Gotcha.
since A is equal to E and E is equal to H because they're vertical, then you know that A is equal to D, A is equal to E, and A is equal to H. But the key was knowing A was equal to E. And I couldn't tell that by determining that they were acute or obtuse. The only reason I knew that is because I know that corresponding angles are equal.
Gotcha.
Hopefully that's cleared up transversals. Now, here's a typical problem that you might get where they would draw that, but then they confuse you by drawing that also. And then they're going to ask you questions about that picture. And the secret is to eliminate the line that is not the transversal that you care about. In other words, this line here is also a transversal, just like this one is. They're both transversals. But if they're asking you questions about, well, they tell you this one's 20, what's this one up here? What's x? What's x in that picture?
Oh, 20.
Right. And it's because this is the transversal. In other words, I took this line here and I kind of eliminated it from my picture.
Could you also keep the triangle there and make a triangle at the 180?
I'm sorry. Well, you could, but we don't know this angle here, and we don't know that angle there. So I really can't figure out what x is based on that. But as long as you tell me that these two lines are parallel, then x has to be 20.
Gotcha.
Now, let's talk about those theorems. There's 4 theorems, right? Alternate interiors are equal, alternate exteriors are equal, correspondings are equal, and consecutives are supplementary. Well, the reverse is true also. In other words, if you don't know these two lines are parallel, but I tell you that this angle is 20 and this angle is 20, that makes them parallel. There's no way these two lines are not parallel once I tell you that that's 20 and that's 20. In other words, all those theorems work in reverse.
Gotcha.
To prove that two lines are parallel. It's not always, you're not always going to get the problem where they tell you the two lines are parallel, which angles are equal, but you'll also come across problems where they tell you the angle is equal. Does that make the lines parallel? Well, if I make that one 21 degrees, these two lines are not parallel, and you know that for certain.
Gotcha.
All right. If you forget those theorems and yet your problem is like that, you can always remember the theorems by drawing a slanted line and now knowing that this one's equal to that one, this one's equal to that one, this one's equal to that one, just because they're the obtuse ones. Well, once you've slanted that line a little bit, it becomes much easier to figure out which angles are equal to one another. So even if you were given this problem, there's nothing that prevents you from, in your head, slanting that line a little bit and figuring out which angles are equal. Once you slant that line, now you know that's x and that's x there, which means that that's x and that's x. In other words, alternate interior angles are equal.
Gotcha.
All right.
Another quick question. What's an opposite reciprocal?
If the slope of a perpendicular, or excuse me, if the slope of a line is 3/2, then the slope of the perpendicular line is the opposite reciprocal. There's two things you have to do. You have to change the sign and you have to flip them. So negative 2/3 is the opposite reciprocal.
Gotcha. Okay.
What if I said the slope was 5? What would the opposite reciprocal be?
-5?
Negative 1/5. Remember, you have to do two things.
Oh, right. I'm sorry.
Always two things. Always. Even if it's a single number with an implied denominator.
Okay.
You still have to find the reciprocal and the opposite reciprocal. And
Gotcha.
that is the relationship between parallel lines, or, excuse me, the slope of a parallel line and the slope of a perpendicular line. In other words, if I give you a slope of 3, right there, that line has a slope of 3, and now I draw a perpendicular line to it. What's the slope of this perpendicular line?
-1/3.
And you can tell that it is. It's certainly negative, and it's less than 1, so it's flatter than a 45-degree angle would be. And
Gotcha.
that's parallel and perpendicular. And
Okay.
so let's see, we finished 30, did we not?
Mm-hmm.
Complete the following proof. Write your two-column proof. The hexagon is regular, and we're trying to prove that angle 1 plus angle 11 is 180 degrees. Well, instead of writing a two-column proof,
Mm-hmm.
I'm just going to explain the rationale. I'm going to give you kind of a paragraph proof.
Okay.
There's actually three kinds of proofs. There's a two-column proof, there's a paragraph proof, and then there's a flow proof.
Okay.
And a two-column proof you're kind of familiar with. And even though this says do a two-column proof, I don't want to spend the time trying to figure out how to do the two-column proof.
Gotcha.
So it wouldn't be that hard. Once I explain how the concept of how we're going to prove that 1 and 11 are supplementary, let me explain it to you, and then I think you'll kind of get the idea. 1 is equal to what over around here?
4.
Okay. And the hexagon is regular. That's a given.
Mm-hmm.
So 4 is equal to what?
5.
It is equal to 5, but we're concerned about these angles over here.
So 9.
4 is equal to 9 because regular hexagons, all the angles are equal to one another.
Gotcha.
And 9 and 11 are what?
Supplementary.
Because they're a linear pair.
Gotcha.
Well, if 4 was equal to 9 and 1 was equal to 4 and 9 is supplementary to 11, then by substitution, or the transitive property actually, then 1 plus 11 must be supplemental. If 9 and 11 are supplementary, then and 1 is equal to 9, then 1 and 11 are supplementary. So we've just proved it. And you could write up a two-column proof with basically those three statements. Well, let's see. The first statement would be 1 is equal to 4, and the reason would be vertical angles are equal. Second one would be 4 is equal to 9. The reason is regular polygons have all equal angles. And third, 9 is supplementary to 11. The reason being linear pairs are supplementary. And finally, 1 is supplementary to 11 because of substitution. In other words, if 9 is supplementary to 11 and 1 is equal to 9, then 1 is supplementary to 11. And finally, 1 plus 11 at 180 degrees, and the reason is definition of supplementary angles.
Gotcha.
Okay. All right, that kind of takes care of that page. And we've got a little over 10 minutes. What else would you like to?
I'm doing also some transformations.
Yeah.
And I have a couple of interesting ones that I don't really understand.
Okay, let me see if I already have a picture here.
Okay.
Not this page, is it?
It is, but it's the other side.
Unfortunately, the student only sent me one page.
Do you want me to send you the other page real quick?
Yeah.
Okay.
Send me the other page. Yeah, that was the one you just sent me. But since now that you've done it, it should be fairly easy to do another one.
Okay.
Tell me when you sent it.
Okay, yeah.
Didn't come in the spam, did it? No. Actually, my phone will probably alert me to it the quickest. My phone usually goes off before I actually see it in my inbox. I know, it's kind of funny why it would be faster. Huh. Haven't gotten it yet. When you sent it, did you type just DA and did it give you my full email as an option that you could just touch then?
Yep.
There it is. Yeah. No, this time it came before my phone went off. Well, I think it's probably easier to do this one because they give you a point instead of X and Y.
Okay.
Just so you can get the idea.
Okay.
If I translate it 1 unit to the right and 6 units down, what's my point if I'm starting here?
Would it be -3, comma -3?
Yep. How about reflected over the x-axis?
Reflected over the x-axis. Is it the starting point or from the last point?
The starting point. In other words, here, let me draw a picture of this because once you draw a picture, it becomes pretty obvious. Whoops, hold on. Let's draw the starting point on there. -4, 3. We'll put it right there. If I reflect that point over the x-axis, it ends up right here. What are the coordinates on that point?
Oh, -4, -3.
Yeah. In other words, you just change the sign on the y-coordinate. If I reflect that about the y-axis, it ends up over there. What's the coordinates on that point?
4, 3.
So you change the sign on the x-coordinate.
Okay.
Rotate it And when they talk rotation here, I think well, oh, I see why they didn't put clockwise or counterclockwise. If it's 180 degrees, you don't need to state whether it's clockwise or counterclockwise.
Gotcha.
Because they're both the same. If it's 90 degrees, notice they have to put in clockwise.
Gotcha.
Let's do the 90-degree one first, clockwise by 90 degrees. How do I do that? I draw a line to the origin, and I rotate that line 90 degrees so that it's right there. In other words, that is a 90-degree angle.
Mm-hmm.
And when you rotate it 90 degrees clockwise,
would it be 3, 4?
Yeah, you can memorize the rules. There's a bunch of rules for these rotations and stuff.
Gotcha.
And one of them, for a 90-degree rotation, you switch the coordinates and you change the sign on one of them.
Gotcha.
Notice that if I rotated it 90 degrees counterclockwise,
would it be -3, -4?
Yeah. In other words, it's going to be the same as that, only with opposite signs on both.
Gotcha.
So for me, rather than memorizing all of those rules, I kind of draw the picture and see if I can figure it out. In other words, I know the numbers aren't going to change. It's just the sign. Well, when I change that point over there, I can tell that both signs are positive. And then when I put it down here, I can tell both signs have to be negative.
Gotcha.
All right, so let's go back and do a 180-degree rotation. And they don't say whether it's clockwise or counterclockwise because it would be the same.
Gotcha.
What are the coordinates on that point?
Would it be 4, -3?
Yes.
Okay.
Not 3, -4. And the way I can tell that is let's make that line much more slopey. In other words, what if my point was right there? Okay. Well, that's going to be like -4, 1. And what is this point over here that you get by rotating it 180 degrees? Well, what are the coordinates on that point?
4, -1.
Right. In other words, a rotation of 180 degrees, you leave the coordinates the same, but you just change their sign.
Gotcha.
And I would never get confused. In other words, it's easy to get confused when my point was at -4, 3. I can't see the solution. When I made it like this, well, I can certainly tell this is not 1, 4 or 1, -4. I know that it's 4, -1 just because I can look at it. So this is a little similar to those parallel lines that as long as that transversal is at a nice angle, you don't need all those theorems. Well, same thing here. As long as my points are far enough away, the absolute values of them, I don't need it. But if I go back and I put the exact point on there, -4, 3, well, now my 180-degree rotation, I can't look at that and tell, is that 4, -3, or could it be 3, -4? I don't know. I can't tell by looking at it.
Right.
So to know the rule, we now know the rule. And the rule is you just switch the signs on the x and the y coordinate. Okay,
Gotcha.
so I know this one isn't right, even though I can't visually see it.
Gotcha.
I know it has to be that one, and the reason I know it is because if I draw that other point, then there's no question about it. Then I can see. And I can see that 180-degree rotation merely requires you to change the sign on both the x and the y coordinate.
Gotcha.
All right. We're reflecting about the x, y, 180. Let's reflect about the line y equal x. Now,
The y equals x?
yeah, here's that line.
Would it be 4, -3?
Well, that's, yeah. This is actually 3, -4.
Okay.
And this is another case where I cannot visually see it. And it's easy to make a mistake. The only reason I happen to know this one is because when you reflect about the line y equal x, that's how you get the inverse of a function. That's exactly how you get the inverse. In other words, if I've got e to the x and I want the inverse of it, I reflect this function across the line y equal x. Notice that's the perfect reflection of that line, right?
Right.
Well, all inverse relationships are reflections about the line y equal x. And I happen to know that when you reflect, or when you find an inverse, what was x is now y, and what was y is now x. So if I have a point up here that's xy, after I reflect it over the line y equal x, that point's going to come in y comma x.
Gotcha.
Just switch the two coordinates.
Okay.
So reflecting about the line y equal x is 3 comma minus 4. Just switch the two.
Okay.
Okay.
Gotcha.
Now reflecting about the line y equal negative x, well, there's that line. Let me erase.
-3, 4?
Yeah. In other words, let's draw that point. Let me get rid of everything else here. There's the line y equal negative x. Our point is -4 comma 3. So a reflection about that line is going to put it on that side over there. What do you suppose that is?
-3, 4?
Switch the two numbers and the signs. So it's -3 comma +4. In other words, I switch the x with the y and I change the sign on both of them.
Gotcha.
And that makes sense. Visually, that even makes sense.
Right.
Once again, you would have no problems if I put a point 1 comma 4. You'd immediately be able to tell visually what the reflection was. It's only tough when these things are close together like they are. In other words, 4 is close to 3, and therefore the reflections are not obvious as what they are. But I've taken you over the time here, so let's end it there unless you have any last questions.
Well, it's one little weird question.
Sure.
But if we were to ask you, if a coordinate was like -3, 3, and they said, what would it be reflected over the line y equals -x? Would it just be the same thing?
Yep. In other words, that coordinate happens to go through that line.
Okay.
Because this line, y equal -x, is a slope of -1, right?
Right.
So I go over 3, up 3. So this point has to lie on that line.
Gotcha.
And if it lies on that line, then it doesn't change when you reflect it over it.
Awesome.
Okay? All right, Connor. Have a good one, and I will talk to you next time.
Sounds good. Thanks for your help.
You're welcome.